Okay, good morning, everyone. Hope you had a good weekend. We are down to our last, let's see, 3 class periods. So we're going to have class today. We're going to have class on Wednesday. We'll have class next Monday, and then our final is next Wednesday. So we had talked about this exam 4, and I'm officially, there's just no way that we're going to be able to squeeze an exam 4 in here. So I think that's a good thing. What I'll do when I'm looking at the grades, what I'll do is I will replace exam 4 on your grades with whatever your highest exam grade is. So everyone will benefit from that. Today, what I want to do, we talked about polynomial functions and their graphs last time. Today, I'd like to talk about rational functions, and maybe, if possible, get into exponential. If not, we'll do exponential and log functions on Wednesday. Okay. So in terms of, go ahead.
I just want to say I lost connection, so I didn't really get to hear what you said about exam 4.
We are not going to have exam 4. And so on your grades, I will replace exam 4 with your highest score that you have on all the exams you take. So if your highest grade is the final, I'll replace 4 with the final. If your highest score is exam 1, I'll replace it with exam 1.
Okay, thank you.
Okay. Now, last class, I ended class by giving you 5 problems to do. And these problems are due on Wednesday. And I will be sending you a Dropbox link probably today or tomorrow, where you can upload those. And I want those turned in before class starts on Wednesday. Are there any questions about how we do these problems? Do you need me to do another example, or are we ready to move on to rational functions?
Would you mind doing another example for us, or one of these?
Yeah. Now, I'm not going to do one of these, but I will do one similar to one of these. Do you want to pick one of these and say, I'd like to see something like that one?
If somebody else has a preference, maybe number 3.
The third one? Okay, let me look at it for a moment.
I don't know if anybody has any ideas.
Yeah, I can do something like the third one, unless somebody else has something. Oops.
Saying for me it was number 2.
That one?
Yeah.
Okay. So I can do something like 2. These are kind of very different in terms of what you have to do to set them equal to 0. So let me do something like number 2. And then if that's not enough, I'll do another one. Okay, so let's sketch the following function. Let's go with negative 4x to the 5th minus 20x cubed. Make that plus 20, sorry. There we go. All right, so we want to sketch this polynomial function. So the first step, you all remember the steps? Do we need to have those up here? We can bring them up. Where are they? Steps, here we go. It was all of this right here. It was this, but then there was other stuff too. So let me go back and get that also. We had this also. All right. Okay, so first step is to figure out the end behavior. And to figure out the end behavior, we're going to be using this table. So for us, step 1, the degree of this polynomial. Someone will tell me what the degree is and what the leading coefficient is.
The degree is 5, the leading coefficient is -4.
-4 and 5. So the degree is the highest power of x, so that's 5. The leading coefficient is negative, so we have an odd degree and we have a negative leading coefficient. So if we're going to do an odd degree, that means that it's going to be either this one or this one of those blue ones. But the leading coefficient being negative means it's either going to be this one or this one. So it has to be this. So we know that the left side must go up and the right side must go down. And in the middle, we have to figure out what's going on. So the next step is to find the x-intercepts. And to do that, we set the entire function equal to 0. So -4x to the 5th plus 20x cubed. Set that equal to 0. And then for this problem, we can factor a greatest common factor. So this depends on you, but I'm going to pull out, I can pull a 4 out and an x cubed. I'm going to pull a -4 x cubed out. And the reason I'm doing -4 is because I want to make this first number a positive number. So pull out that. Someone want to tell me what I'm left with when I pull out a -x cubed or -4x cubed? What would still be here?
Is it x squared plus 5?
X squared minus 5. Because you need the negative to distribute through and get you a positive 20, right?
Oh, okay.
Yeah. So you could have, if you wanted to, you could have done this. You could have pulled out a 4x cubed, and then you'd been left with -x squared plus 5 equals 0. Both of those would work. I'm going to continue with the one on the left, though. So this is, I think, the tricky part of the problem is how do you go from here? We've factored, so we know that we can set this equal to 0. And we know we can set this equal to 0. Right, like that. So we get 2 solutions. Here you could divide both sides by -4. If you divide this side by -4 and divide this side by -4, you get x cubed to 0. And the only number that you can cube and get 0 is 0 itself. So we get one answer is 0. This is the tricky one, okay? So let me just clarify something. Had that been x squared minus 9 equals 0, had it been, it's not, but had it been this, then everyone here would have to recognize that this is a difference of squares. Does that seem okay to you? We've done that a few times. So here, the problem is 5 is not a perfect square, right? 5 is not a perfect square. So I'm going to try and show you one more thing. If it was x squared, let's say minus 16 equals 0, you would say x plus 4x minus 4 equals 0. Again, using the difference of squares formula. So notice in both of these, whatever this number is, I'm just putting the square root of it here. So the square root of 9 is 3. So I put 3 here and 3 here, plus in front of one and minus in front of the other. Here, same thing, 16, 4, and 4, because the square root of 16 is 4. Do you see that this one, as a difference of squares, should be x plus something, x minus something, but 5 isn't a perfect square, right? The square root of 5 isn't a number that we just know, is it? Do y'all agree with that? Like 9 and 16, we know the square roots of those?
Yeah.
But would you agree with this? I could put square root of 5 and square root of 5 here. In other words, I don't know what it is off the top of my head, but my calculator knows, right? My calculator knows what the square root of 5 is. So this is usually very strange in a college algebra class if you've never done this before. It does not have to be a perfect square to be able to use the difference of squares formula. It can be any number. And all you have to do is put the square root of that number there. I'll give you one more example. If we had, let's say we had x squared minus 10, we could break that down to be x plus root 10 x minus root 10, even though I don't know what the square root of 10 is off the top of my head. Does that make sense, everyone? We can,
Yes.
yes, no questions? So with that, I can actually now take each of these and set them equal to 0. So I can set x plus root 5 equal to 0, x minus root 5 equal to 0. And then if I subtract the root 5, I get negative root 5 here, and over here I get positive root 5. And I think I'll just get on my calculator and figure out what that is. So I'm going to take the square root of 5 now. I get about 2.2, I'll say. So x is about negative 2.2, and x is positive 2.2. So I have 3 x-intercepts. Once we have found the x-intercepts, we need to find the multiplicity of the factors and determine if we cross or bounce at each of these x-intercepts. So this is the tricky part, because what you have to do is focus your attention on when we had the factors written out, and this is the blue parts. So here, the power on this factor is 3, that's odd. And what happens if you have an odd multiplicity? I put that up here. If the power is odd, what do we do there?
Oh, we cross.
Cross. So we're going to cross when we get to that x-intercept. And then on these two, that's a 1 here and a 1 here. You have to be real careful. You can't use this because here x squared minus 4 is not factored. You can only get your multiplicity after it's factored. Once it's factored, then we can see that this is a 1 and that's a 1. So that means we're going to cross here because 1 is odd. And we're going to cross here because 1 is odd. So we're crossing at all the x-intercepts. I think I'm ready to draw. Are there any questions while I'm setting this up?
I have a question.
Yes.
What we're learning about today, is it going to build off of this?
A little bit, yeah, a little bit. It's going to be a completely different technique, okay? Like we have to have a different set of steps, but there are some things that we've learned here that we're going to need for the next part. Can I ask why you're asking?
Because I feel like I've been kind of confident in everything we've learned up until this lesson.
Yeah, no, I understand that.
It's not bad, but you know.
Yeah, no, I understand. Yeah, polynomial functions are definitely a little more challenging than quadratics and lines. And rational functions, I think, are the hardest out of all of them. So I think that the next one will be even a little bit scary, more scary than this, but we're going to keep it, we're going to try and keep it as simple as we can because it can get really, really bad, but we're going to try and keep it nice. Okay, so now here we go. I'm going to put my x-intercepts 0 here. That's that one right there. And then I have negative 2.2. So I'm going to just go like negative, that's root 5. That's about negative 2.2, whatever, right there. The other one's positive root 5, so I'll put it there. And now I know that my, what was it, left side went up, right side went down, right, from here. So I know that my graph, when I draw it, it's going to have to go up over here and down over here. And as I draw this, I have to cross through at each one. So I'm going to cross through, cross through, and connect. Nice and smooth, right? Remember, polynomials are smooth and curved. And we talked last time that everyone can have a different picture, right? Someone else could draw this, and that would be okay, right? We all just have to have the same end behavior. We all have to have the same x-intercepts, and we all have to have the same crossing or bouncing happening. As long as that's consistent, you're good. Okay, what do y'all think? Should we do another one, or it's up to y'all? I mean, this is what you'll be tested on. So if you feel like I've given you enough, we can move on. If not, then we can do one more. Should I? Why don't I take a poll? I'll take a poll real quick. I'm going to go refill my drink, and while I'm doing that, you can tell me yes, you want to see one more, No, you're ready to move on. Be right back. Okay, so we have an overwhelming 80% that want to see another example. So let's do another one.
I have a question.
Yes.
If we got the same thing, but like in between the brackets, it was x plus a number, but you cannot get it into two brackets.
What? Say again?
Like there was a question where I got like in the brackets, x squared plus 25. So it's not difference between two squares. So what am I supposed to do next?
Ah, okay. So which one was that?
Just a minute.
You're talking about on one of the problems
There were two actually. It was number 5 and number a minute.
So
Number
you got a plus on number 5?
Yeah, in the brackets it was a plus, and also number 2 I got a plus in the brackets.
So yeah, on this one, on 2, you should get a plus. Okay, so I don't want to go through these problems, like I said, but let's just talk about this first, this one right here. I'm just going to go to step 2, where you set it equal to 0, right?
Yes.
Okay. All right, so what did you factor out?
I did negative 5x squared.
Negative 5x squared, and then inside you're saying you had x squared
Plus 3.
plus 3 equals 0. Okay, good. Now this is a really good question, all right? Because this x squared plus 3, what you're asking is, you know, what do I do with this? Because it does not look like x squared minus 3, which would be a difference of squares, right? That would be this, plus root 3, x minus root 3. Because there's a minus, you can do the formula difference of squares. So Dean is asking, what happens if there's a plus in between? And if there's a plus, that means it can't be factored. You cannot break this down. So this is actually a really important question. What I was hoping you would see in this is think about what we're asking ourselves. We're asking ourselves, when is this equal to 0, right? When is that equal to 0? Well, that's going to happen when this is 0 or when this is 0. One of those would have to be 0 in order for this to be true. This would be 0 if x is 0. You'll agree with that? If x is 0, then negative 5 times 0 squared, that's 0, and that would work. Is there anything, though, here that you could ever plug in here to get 0? So think about what would happen if you plugged a number in here. Anytime you square a number, what happens to it? Is it positive or negative?
Positive.
Positive. Well, you could plug in 0, and then 0 squared would be 0, but if it's a number other than 0, you're going to get a positive number here, right? And then you're adding 3 to it. So no matter what you ever plug in, ever, there's no way that that could ever be 0, right? In other words, there's no solution for this. There's no way to make that 0. Which means that, you know, when you go to graph it, you only have one x-intercept. This one right here. You only have one. You'll still have whatever left and right hand behavior you have, okay? You'll have one x-intercept at 0, Now the crossing and bouncing you still have to figure out, but that can just be determined by the squared here. Now on number 5, you should not get a plus. Because if you take that and set it equal to 0.
Yeah, that's my bad. I copied the equation as in it was a
Okay.
plus in the beginning,
Okay,
so I
yeah.
just figured that out.
Yeah, that one will be a difference of squares, and it will be x squared minus 25, and that will break down. Good questions. Okay, so people still want to see a problem, so let me try something else. I'll do something a little more like number, which one was it, Bela? Did you say that you want to see something like 3?
Yes, please.
Like 3, okay. So let me look at 3 just to get an idea of what's going on here. 3, okay. All right, let me just make one up real quick. I want to make sure that it looks something like that. It may not look exactly like this, but it has the same sort of principles involved when it comes to how you do it. Okay, so here we go. Negative 3x to the 4th plus 21x cubed minus 36x squared. All right, so I'm not even going to show this step. Step 1, it should go down and down, and in the middle, who knows? Okay. So I'm going to trust that you could all get that on your own. Is that all right? Off the table? You all right?
Yes.
Okay. All right. The x-intercepts are always the hardest part on these. So what we're going to do now, set it equal to 0. All right. Let's try and see if we can pull a number out of here. 3 goes into all of these, right? And because this first one is negative, I'm going to pull a negative 3 out. And then I also noticed that there's an x squared in all of these. That's the biggest or highest power of x that I have in all of them. So if I pull out a negative 3x squared, I will be left with an x squared plus minus 7x. And then plus, let's see, that goes in there, what, 12 times? Is that right? 3 goes in there 12 times. That's it. So basically I pulled a negative, I divided each of these by negative 3. That's how I got these numbers. And then I reduced the power of x by 2 on each of those. Now in this parenthesis right here, we need to be able to do that little thing where we factor. So this is where you take the number back here, 12, and you take the number in the middle, negative 7, and you have to come up with 2 numbers that multiply to be 12, but add up to be negative 7. Can somebody tell me what numbers those are? Multiply to be 12, add to be negative 7.
Is it -3 and -4?
Negative 3 and negative 4, very good. Negative 3 times negative 4 gives you positive 12. Negative 3 plus negative 4 gives you negative 7. Very good. So that means that this will break down to be x minus 3, x minus 4. And then you can just set each of these equal to 0. So if you set that equal to 0, set that to 0, set that to 0, you should get 3 answers, 0, 3, and 4. Those are your x-intercepts. And now you want to look at crossing or bouncing. So you look at the powers on the factors. There's a 2 here, there's a 1 here, there's a 1 here. So that 2 tells you what? What does the 2 tell you? What are you gonna do here?
That you're gonna bounce.
Bounce. So we're gonna bounce off that one. And then these are 1s, right? Those are odd numbers, so we're gonna cross. So then you just go to draw your picture. 0, let me do it in a different color. 0, you have an x-intercept. At 3, you have an x-intercept. And at 4, you have an x-intercept. Both sides go down. So when I draw this, it's going to be down this way, down that way. And I only bounce at 0. So when I draw this and I come up to this, I'm going to have to bounce off. I do not want to cross through. So I'm going to just go up. And you might have to erase and kind of like start it over to make it look right, to make it work. So I'm going to bounce off of that, come down as far as I want. I'm going to go back up and I'm going to cross through at 3, go up as far as I want, come back down, nice and curved, smooth, cross through, connect. I'm done. Okay. All right. One thing I did not talk about last time that I think is kind of important is that, you know, when we've been studying functions, you know, we started with lines, and then after that we did quadratics or parabolas, whatever, quadratic. And now we're doing polynomials. And I even told you last time that a line is a polynomial and a quadratic is a polynomial, but this is the way we study them. We start with lines, then quadratic, then we go to the higher degrees. All of these have special purposes, like in the real world. Like lines are good at modeling certain things. Like if you make a certain amount of money per hour or electricity charges, I gave you examples of when we use lines in the real world. Quadratics, I talked about also in the real world, you know, parabolas are all over the place, right? I talked about satellites and flashlights and all these different places that parabolas occur. What I haven't talked about, or what I didn't mention last time, is when do polynomials come into play? So, you know, when do you see things in the real world, you know, that do something like this, you know? When does that happen? Like, when is a polynomial good at showing something? Well, you can imagine there's tons of things, right? I mean, just look at, let me see, let me bring something up here. Trying to get an image here for us to look at. Here we go. So I just typed into Google, you know, the stock market in the last 20 years, you know, historical graph. If you look at this, the stock market, you can imagine that this, you know, kind of looks like, you know, it is jagged, but if you were to connect everything with a smooth curve, this thing behaves kind of like a polynomial function. So what we do in the real world is we take data and then we try and figure out what polynomial function that is. And you can try and fit a polynomial function to the data. And we do that all the time. We meaning people who are interested in this, financial advisors, things like that. And you can try and predict things. Another one, let's see, interest rates. Fannie Mae interest rates. So right now, I don't know how many of you are in the market to buy a house right now, but if you were in the market to buy a house, you could see what the interest rates are over the past, let's see, this is the past year. Y'all know what an interest rate is? I mean, I don't want to get too deep into this, but when you buy a house, most people don't have enough money to just buy a house, right? You just don't have $300,000 sitting in the bank. So you go to a bank, say, I'd like to borrow $300,000. And they say, okay, here's the money, but you're going to pay back more than you're borrowing from us. And there's an interest rate, which basically determines how much more you're going to have to pay them back than you borrowed. And if you look at this year, I don't know if you've heard about this, but right now interest rates are at a historic low. They're very, very low. So this is the past year. You can see they're different graphs because it depends on if you want to borrow money for 30 years or for 15 years, depends on how long you want to borrow the money for. Here's the past 3 years. That kind of really illustrates how low the interest rates have dropped, right? But do y'all see that this is kind of like a polynomial? See, I mean, it's not smooth, but if you just look at it on an average, it's it's definitely not a line. It's definitely not a parabola, right? It's more like a polynomial. Here it is over the past 5 years. Here it is over the past 10 years. And here's all time as long as they've been keeping records, which goes back to like the 1970s. So look at that. When they're saying interest rates are historic low, you can see it here, right? I mean, it is historically a low. Back in the 1970s, if you wanted to go buy a house, your interest rate, there was a time, let's see, 1981, interest rates 18%. That's like a credit card. That's how ridiculously high that interest rate is. So now it's at a little over 2%, right? A little over 2%. My point is, we can get into all financial talk. My point is, if you look at this, polynomial function, okay? That's where these come into play. So I just wanted to show you, just so that you understand that like in the real world, polynomials are something that are important for people to study. Now, the next type of function that we're going to study is called a rational function. Are y'all ready to move on? I think we have to at some point move on. So y'all ready to talk about rational functions?
I have a quick question.
Yes.
How are you like sure when something has no solution?
Okay, so like the one we did earlier,
Yes.
the way that I knew that there was no solution right there, here's what you could have done. Let me back this up. I thought about doing this. I wanted to just have you think through it, but just try and set that equal to 0. Okay. Try and set that equal to 0. And then move the 3 to the other side. And then think about what you're asking yourself here. What number squared is -3? Well, what do you know about squaring a number? No matter what, right? Take any number and multiply it times itself, your answer must be positive, shouldn't it? Yes?
Okay, I see.
Katrina, do you understand that?
Yes.
Like, this can't ever happen. Now, it can happen if you use imaginary numbers. If in high school you may have learned about imaginary numbers, we are not dealing with imaginary numbers at all. We're not talking about them. We're not doing anything with them. That's a different class, okay? So for here, we're just going to say here, no solution. Does that help you see how you would know that?
Yes, so it has to be a positive on the, okay, I understand.
This is only because it was an x squared. Had this been, just x, then of course your answer would just be -3. You just move the 3 over, you're done. It's the fact that it's x squared has to be -3 tells you it can't happen.
Okay, thank you.
Okay. All right. So now, rational functions. So I think what I'm going to do for rational functions, is I'm actually going to start by kind of explaining where they're used in the real world. And then we'll start looking at them instead of us doing everything and then me telling you where they're used. So I'm going to share something with you here. I'm going to write something down here. This is a movie quote. So I'm going to see if anyone in this class can tell me what movie this is from. And I'm kind of, well, maybe I'll go look it up and that way I can quote it exactly. Here we go. Try and do it without giving away the movie here. Here we go. Here we go. So this is a quote from a movie. Let's see if anyone can tell me what movie this is. I don't expect anyone to get this. The older I've gotten, the fewer students have been able to get this. It's kind of an older movie. So on a long enough timeline, the survival rate for everything drops to 0. So let's try and understand what the quote was saying first, and then I'll tell you the movie if nobody knows it. So let's say that we had a graph that represented here time, okay? And maybe this is measured in years. And then this is what I'm going to call the survival rate. Think about the survival rate as like a measurement of the probability that something is still living. Okay, so let's just think about humans for a moment. Okay, say that a human is born, all right, and we're not going to have a debate about when that begins or when life begins. We're not going there. Let's just say that we all agree we have a living human being, and let's say that's time equals 0. Generally speaking, do you all feel like the chances that a baby will live to be 1 year old is pretty good? Just in general, I'm not talking about, of course, some kids, they die, but just if a baby is born, a human being is born, the chance that they'll live to see 1 year old is pretty good. Yes, would y'all agree?
Yes.
Yes, okay. So I'm gonna put 1 here. So let's say up here, I'm going to put 100% to mean guaranteed they'll be alive. So could you say that 100% they will live to be 1? Can't say 100%, right? Like some kids will not reach the age of 1, but most will. So I'm going to say at 1 year old, let's say it's a really high probability, maybe in the 90% or so. Okay. Do you think that the average human will live to turn 10 years old? Pretty good probability? Still pretty high? Maybe not as high as 1, but maybe 10. Okay. What about let's crank it up a little bit. How about 60? Is that going to be as high as 1 or 10? The probability that someone makes it to 60?
No.
No, it's lower, right? It's got to be lower. And here's where things start getting really interesting though. What about 80? Good chance to live to 80? It depends on if you're a man or a woman and where you're, what part of the world you're in also. But I'm just saying, just human beings on this planet. A lot of people make it to 80 these days, right? I mean, a lot of people do. But would you agree that it's got to be less than 60? Like you have a better chance of living to 60 than you do to 80, right? So maybe it's dropped down. Okay, here's where things get really kind of, I think, interesting. Let's talk about 100. How about the probability of living out to be 100 years old? It's gotten smaller, right? I mean, it could happen, right? It could happen, but now you're getting into a smaller chance. In fact, my wife's grandpa just turned 103, like 2 or 3 days ago, 4 days ago, last week. So people live to be 100. It's just a really, small group that reached that. Okay, now let's get crazy. How about 120?
I know that's very low.
Sorry?
I said that survival rate is very low.
Yeah, okay, so is it very low or is it impossible?
I don't know if we've had anybody live to 120 yet.
Yeah, I don't
It's not
know.
impossible. It's not impossible, but it is low.
Okay, yeah, so see, what we're talking about is a probability here. We're not talking about has it ever happened. Now, it has probably never happened. I don't know, we have to look up the Guinness Book of World Records, but in terms of probability, it's very low chance that you're gonna live to be 120. I don't think anyone here really wants to live to be that old, actually, because when you get to this age, you look a lot like you do back here at 0, you know, basically everyone's taking care of you. So let's see, 120, very low probability. You'll see my dot there. How about this? 200.
That's ancient.
Can you tell me that there is 0 chance of that happening? 0 chance. Or is there some chance that someone could live to be 200?
Not a human.
You don't think so?
I don't think a human can live to be 200. I know a human couldn't live to be 200.
Impossible though? Like, could
Yeah.
I say there is 0 chance of that happening? Could I say
Yep.
that?
Yep.
Okay. So Darshil thinks we can say 0 for 200. All right, then let me ask you this, Darshil. Am I saying your name right?
Yes.
Okay, Darshil, let me ask you this. What about 199? 1 year before that, is that impossible?
I think so. Yes.
Okay, but you said 120, there was a small chance.
Yes.
So when does it become 0
At 121.
then? You see, so I'm challenging your idea here because 121 is kind of arbitrary too, right? I mean, you can't say 121, but it seems like at 120, there is some chance. So where would you ever say 0? Like you would have to pick, and it's not really reasonable to pick a number. So think about this, Darshil, I'm going to challenge you again. And I'm challenging the whole class by this. Darshil's saying 200 is impossible, okay? So Darshil, what do you think is more possible? What do you think of these 2 scenarios is more likely? I live to be 200, okay, that's one scenario. What are the chances of that happening versus this? So tell me how improbable this sounds. That I'm gonna win the lottery tonight, okay? What do you think of those 2 is more probable? That I live to be 200, that I win the lottery?
Winning the lottery is more
Winning the
probable.
lottery would be more probable, wouldn't it? Okay.
Yes.
Start over. Me living to be 200 or me winning the lottery tonight and getting struck by lightning and surviving. So could I win the lottery tonight and get struck by lightning and survive? Could it happen?
Yes, that could happen.
What are the chances of that happening?
Good and bad luck. Everything happens for a reason.
But it could happen, right? So there's this like really, really small chance that I could win the lottery and get struck by lightning and survive, right? It's a really small chance it could happen.
Yes.
All right. So that's still more likely than me living to be 200, right?
Yes, sir.
Okay. Now, what do you think about this? Me living to be 200 or me winning the lottery tonight, getting struck by lightning and surviving, and then me winning the lottery the next day and getting struck by lightning again and surviving.
Wow.
So could it happen? Could it happen? Could I win the lottery tonight, get struck by lightning, survive, the next day win the lottery again and get struck by lightning again? Could those events happen?
Those events could happen.
They could, right? And so there's this what we call infinitesimal chance of it happening, right? And that's what I'm getting at. This 200 right here, this 200, even though it is infinitesimally small chance of somebody living to be 200, it is something, and it's not 0, but it could be so small that it would be like me getting hit by lightning every day for the rest of my life. Like, could it happen? Yes, but is it going to happen? I mean, infinitesimally small. So this is what this quote is about. On a long enough timeline, the survival rate for everything drops to 0, meaning no matter what we're talking about, whether it be a human or a butterfly or a bird or a lizard, it doesn't matter what it is, the survival rates for everything drop to 0. But the important part is when you look at this out here, if you were to zoom in and look at what's happening here, the graph would be getting closer and closer to 0, but it would never touch. It would approach 0 and just get closer and closer and closer and closer without ever actually hitting it. Does that make sense? The further out you go, the closer it is. And I'll show you a picture. I'll show everyone a picture of this, okay? I'm about to give away the movie is Fight Club. If you've ever seen Fight Club, it's from the movie Fight Club. So he's an insurance adjuster. He does things for insurance company for cars, and they talk about it in the movie anyway. All right, so let me see here. I want to graph something for you. This is your first look at a rational function. I'm gonna have you look at the most basic one. This is what it looks like. Here's the graph. And what I want you to see is that this graph, if you start to go to the right, do you see what it's doing? Do you see that as you go to the right, it's getting closer and closer to the x-axis? It's getting closer and closer to 0. I'm going to zoom in. Let me see here. Do y'all see the y value? You see the y value is 0.06. That's a small number. But as I go further and further to the right, let me go way out here. Go out here to like 100 or so. Out here, now it's 0.01, so it's really small. But see, there is a space in there. If I zoom in, you can see the space. Zoom back out, way out, and I'm going to go way out here to like. Let's go out to like 20,000 or so. Let's zoom in here. See, that graph looks like it's on the x-axis, but it's not. I got to get way in here though. There it is. Okay, see, I've got a little space in there. So you can see, look at the value, 0.000049. Really small, but something, right? It's not 0. And that's exactly what we mean by this idea of approaching 0. Does this all make sense? Kind of what I'm trying to get you to see, the idea of a graph getting closer to something without actually ever getting there. And that is one of the main characteristics of a rational function. Okay, so in rational functions, you have some important characteristics. Rational functions have, I should say can have, but I'm just going to put have what are called vertical I'm going to write the word down first, then I'll say it. Okay, rational functions have these things called vertical asymptotes and horizontal asymptotes. This word asymptotes is a weird word because the M is silent and the P is silent. Well, the M's there, but the P is silent. So asymptotes. It's hard to pronounce, asymptotes. But these are two of the main characteristics of rational functions that lines, quadratics, and polynomials don't have. All right, so when it comes to the real world, of course, lines, quadratics, and polynomials have important uses in the real world, but there are certain things that we look at in the real world where these won't work. And that's where rational functions come in. They can help us model things that start to go down, get closer to something. You could do the same thing with something like, think about your phone, right? Think about your phone. Like you bought your phone, bring it home from the store, it's all shiny and brand new and you're playing with it, everything. You know it's gonna work, right? You just bought it, everything's great. What's the probability it's gonna work tomorrow? Pretty good, right? What's the probability it's gonna work the next day? Pretty good. What's probably it's gonna work in a year? Probably pretty good. How about in 5 years? It starts to get smaller, right? What's the probability it's going to work in 10 years? I don't know. The battery's probably not going to work anymore. So things start to drop down. Everything that we use, you know, your car, your tires, on your vehicle, light bulbs in your house, everything has this model where it drops, the probability of it working drops down. Okay, you can't put a specific time when it's going to fail. So the further you go out, the closer it gets to 0. So only rational functions, well, up to this point, only rational functions will allow us to model that behavior. Okay, let me get back to the picture. I want to show you something here. Zoom back out. Okay, so when we were looking at this graph, here's what it looked like, right? So notice that as we go to the right, this thing gets smaller and smaller and approaches the x-axis. Also, if we go to the left, y'all see that it flattens out and approaches the x-axis. See that right there? Both sides. Remember with polynomials, what happened with polynomials? The ones we were studying before this. They either were like this, or like that, or like that, or like that, right? There was only like 4 possibilities with polynomials. With rational functions, you have this flattening out behavior, which is very different than the polynomial. Also, look in the middle of this graph. There's something interesting happening here. Notice that as we get closer to 0, the graph is headed up and up and up, and it actually, like we call it, blows up. It blows up. It just takes off to infinity. And on the other side of 0, it takes off and goes down like this. It takes off to negative infinity. And so these are very different characteristics than anything we've seen before. So we have to start to come up with a way of how could I give you a function and then you go graph it and get something like this, right? So we need to start setting up the steps. And it's going to be a pretty big challenge for us, all right? So let's see. I want to just show you on a picture. If we have a rational function that goes like this and like this, anywhere it flattens out, I want you to imagine that there's this dotted line. I'm going to do it in a different color. A dotted line this way and a dotted line this way. This dotted line is what we call the horizontal asymptote. And the way that I think you should think about it is this. A horizontal asymptote is a dotted line which acts like a magnet pulling the function toward it, towards it, whatever. So it's kind of like when you're drawing your graph, this dotted line here is like a magnet. As you're trying to draw your graph, you're getting pulled towards the dotted line as you go out to the edges. Okay, this right here is all end behavior only. It only tells you what's happening at the ends. Here, it's getting pulled to the left. The function is getting pulled towards that dotted line. Do you understand the basic idea of a horizontal asymptote? It gives you what's happening at the ends and it pulls your graph towards it. Then you have something very interesting happening here. This vertical line, see that? What happens is, like, think about if you were trying to draw this, okay? You have your pen, you're trying to draw the graph, and then what happens? This blue vertical line is almost like a barrier. And as you get closer to it, your graph's like, oh, I can't hit that. I can't hit that. I need to go somewhere. So the graph starts to go down and just gets closer and closer to the barrier, but never touches it. And it does that from both sides. From one side, it went down, the other side, it's going up. So this is known as a vertical, not horizontal, asymptote. And this is a vertical barrier. barrier. Okay, you can't cross it. It forces your function up or down. Okay. Y'all doing all right? So all I want you to know from this is that all rational functions have these things called horizontal and vertical asymptotes, and how they impact the way you draw the graph. The horizontals are magnets that pull your ends down. Vertical asymptotes are barriers that force your function to go up or down. Now, the big question is, how do we find them? If somebody gives us a function, how do we find them? So I think I'm ready to start giving you the steps to graph these. Steps. You know what? No, I'm not going to do that yet. What is a rational function, right? So what do they look like? You know, what do they actually look like when you write them out? So a rational function is, golly, Robert, is just this. It's a function, f of x, where you take a polynomial and simply divide it by a polynomial. So we just studied polynomials, right? Bela was asking, you know, are we going to be doing this stuff for the next thing? And I said, kind of. Well, we kind of are, because what we're going to be doing is taking a polynomial like we were just doing and taking a completely different one and dividing them together. And that's what creates a rational function. The word rational comes from the word ratio, and ratio meaning fraction. So a rational function is a function that is made by creating a fraction out of polynomials. And that's what it is, okay? I'll give you some examples of rational functions. F of x equals x plus 1 over x squared minus 4. That is an example of a rational function. I'll give you another example. X squared minus 4 over x plus 1. And I'll give you one more. X squared minus 4 over x squared minus 8x. These are all examples of rational functions. And the way you know is because if you look at the numerator, the top, that's a polynomial, right? X plus 1 is a line. A line is a polynomial. X squared minus 4 is a quadratic. That's also a polynomial. So you have two polynomials being divided. Polynomial divided by polynomial. Polynomial divided by polynomial. Do you all see that? That's all a rational function is, just the ratio of two polynomials. Any questions? Y'all gotten really quiet on me. Must be your excitement. You ready for the steps to sketch these? It's time for the steps. How to sketch a rational function. Okay, first step is we're going to find the x-intercepts. So remember with polynomials, what we did is we looked at the you know, what happens on that table, right? No tables here. You cannot use tables for rational functions. That's only for polynomials. So the first step we're going to do is we're going to find the x-intercepts. Now the x-intercepts are wherever the graph hits the x-axis. So to do this, this is very important. All you do is set the numerator equal to 0 and solve. So if you want to know where a rational function crosses the x-axis, you have to set the numerator equal to 0 and solve it. The next thing we're going to do is find the vertical asymptotes. And to do that, we will set the denominator equal to 0 and solve. So when you think about what I'm asking you to do here, to sketch a rational function, you're going to just look at the top, set it equal to 0 and solve it. Then you're going to look at the bottom, you're going to set it equal to solve it. And that'll give you both your x-intercepts and vertical asymptotes. And then the last step, and this is the hardest step, is you will find the horizontal asymptotes by comparing the degree of numerator to degree of denominator. Okay, so I have to explain this more. I will explain more as we work through some examples. So I want to fill in step 3. Okay, I want to fill in step 3 after we do a couple of examples. Now, the 4th step is to plot all information from steps 1 through 3. Step 5 is test points. And step 6 is use your brain to sketch. All right. I promised Bela this would be the hardest thing. It's going to be the hardest thing. Here are the steps. Don't worry about like what each step is right now. Let's work through some examples. I think once we do some examples, you'll start to see each of these steps come to light. You ready for this? No? I'll do the first one. Let's do this one, x plus 1 over x squared minus 4. So we're going to do these steps for the function f of x equals x plus 1 over x squared minus 4. All right, here we go. First step. Maybe I should call on people. I feel like I should call on people. Let me bring up my roster thing. I haven't called on people in a while. Off my list here. All right. Evelyn? Is there Evelyn? No. Juliet? You with us?
Yes.
Okay, can you help me with step 1?
Yeah.
Okay. Step 1, we're finding the x-intercepts. So what are we gonna do?
Put it equal to 0.
Okay, just the top though, right? Just the top. So what tell me what the equation I need to write down is for step 1.
X plus 1 equals 0.
There we go, okay. Pretty straightforward, yes. Solve for x. So what would you get there, Julia?
-1.
-1. X is -1. Just move the 1 over. Okay, good. Juliet, you did so good on that one. How about you get us going on the second step?
Okay. Then just do the bottom, which would be x squared minus 4 equals 0.
Okay, and do you recognize x squared minus 4?
Yeah, so you can't solve that, right?
If it was a plus, you couldn't. But since it's a minus, it is a difference of 2 squares. So this is where it turns into 2 things. What would they be? Lily, you can help if you're there. Lily here?
I'm a little confused on what you're asking.
So this difference of squares is going to come up a lot. It's come up on the homework. It's also going to come up during the test. So everyone needs to make sure they're comfortable with this. Diane, it looks like you wanted to chime in.
-2 and +2.
X plus 2 and x minus 2. So that's the way this factors. And then you can set each of these equal to 0.
Oh, okay.
Does
I
that look a
thought-
little more familiar now, Juliet?
Yeah, I was only confused because I thought that something had to go in front of the parentheses.
Gotcha. So when we solve these, we'll get two answers, -2 and +2. Okay, good. Thank you, Juliet.
Mhm.
All right. So Lily, are you there? or No.
Yes.
Okay. So Lily, we have done which steps here?
1 and 2.
1 and 2. So now it's time for step 3, which is to find the horizontal asymptotes by comparing the degree of the numerator and the degree of the denominator. And Lily, I have not given you the steps to do this, have I? I've not told you what to do.
No.
No, but I'm about to. Okay, you ready? So
Sure.
Lily, can you tell me what is the degree of the numerator? So focus all of your attention on the numerator. What is the degree of that? Do you
1.
know what I mean by degree?
Yes. 1.
1. Yeah, that's the highest power of x, right? It's 1. Okay, so I'm going to put that here. The degree, and this is step 3, by the way. The degree of the numerator, I'm going to abbreviate that, is equal to 1. Okay, Lily, what's the degree of the denominator?
2.
2. That's the highest power of x on the bottom. Everyone see that? Yes? So for every problem that you ever do, that's a rational function, you will always compare the degree of the numerator and denominator to one another. How many different scenarios could we have? If we had, we're always going to have 2 numbers, right? 1 and 2. Those numbers can either be different, right? They can be the same, right? If here's the comparison you want to make, okay? This is the step I didn't put here, right? If the numerator's degree is less than the denominator's degree, then the x-axis is your horizontal asymptote. Okay, that's one thing that can happen. So right now, Lily, the degree of the numerator you said is 1, right?
Mm-hmm.
And that is smaller than 2, isn't it?
Yes.
And I'm telling you that if the numerator's degree is smaller than the denominator's degree, then the x-axis is where you're going to have that dotted magnet. Okay? Got me?
Yes.
Now, if, Lily, the degree of the numerator is greater than the denominator, if it were the other way around, like had this been a 2 and that been a 1, then you have no horizontal asymptotes. I'm putting HA for horizontal asymptotes. I'm abbreviating this with HA. No horizontal asymptotes exist. Okay, I'm telling you this. You all have to take this on faith now because I'm telling you this is the way it goes. Right? So if the degree of the numerator is smaller than denominator, the x-axis will be your horizontal asymptote. If it's the other way around, you won't have a horizontal asymptote. And the last thing that could happen is if they're equal. If the numerator is equal to the denominator, then, and I'm going to say ... I will tell you what happens here when we get to an example. Okay, I'm not ready to share that with you yet. So Lily, we are going to call these different cases, all right? I want to call this case A, case B, and case C. Those are the 3 different things that can happen when we do step 3. So Lily, we're in case A, B, or C here for us.
A.
A, right? So we are in case A, which means that the x-axis is the horizontal asymptote. Okay, Lily, you're off the hook. Thank you for doing that. Lewis, are you here? Lewis was here. I guess I bored him. Okay. Jamal, are you here? No, Jamal. Caitlin? No, Caitlin. Hey, by the way, Cheyenne, I see that you are here. I will get that grade updated. I just got real tied up this morning with some stuff. Okay, so Caitlin's not here. Katrina?
Yes, I'm here.
Okay, all right, Katrina, I think you've already participated, but what's step 4, Katrina?
To plot the points.
Plot all the information, right? We got to put everything we gathered together, right? Okay, this is a critical step because Katrina, you have to know what we're doing here in terms of what we're drawing on the graph. So Katrina, what was step 1? What were we finding in step 1?
The X-intercepts.
X-intercepts. So right here, this step 1, that's an X-intercept. That is a point. Those are points. That's a point or points on the X-axis. Right? That's what that is. Now, step 2, those are vertical asymptotes. These are your vertical barriers. And then step 3, the X-axis there, that's your horizontal magnet. Katrina, does that make sense?
Kind of.
Like those are 3 different parts of our graph. They're not all points on the graph, right? These are like characteristics, things that are going to help us draw the graph as opposed to all being just points. So here we go. I'm going to put a graph up here for us. Okay, so Katrina, here we go. Start with the first thing. We have an X-intercept at -1. So that's going to be a dot, right? I'm going to just draw a dot on the X-axis at -1. That seem fair to you?
Yes.
Okay, -1 here. I'm going to put a dot right there. That's the first step. The second step are vertical barriers. And how many will I have, Katrina?
2.
2 of them, right? Now, Katrina, these are not technically like part of the graph. These are barriers that when we draw the function, we can't hit them. So I'm going to go to -2. I'm not going to draw a dot. I'm going to draw a vertical dotted line. And I'm doing it in gray because I want everyone to realize this is not part of my graph. This is something that's going to help me graph the function. It's a vertical barrier that my graph will not be able to cross. It's going to have to go up or down when we get to it. And I
Is
have
this
a
step
second-
4? I'm sorry.
This is
Is this
we're
step
doing
4?
Step 4 is to plot all the information. Yes.
Okay. Okay.
So here's 2. I'm going to draw another vertical barrier at 2 because we had 2 vertical barriers. And then step 3 said that the X-axis is this horizontal magnet. And so watch the way I do this. Towards the end, I'm going to put a dotted line. And on the other end, I'm going to put a dotted line. Those are my horizontal asymptotes. That's my horizontal asymptote. Notice I did not draw a dotted line through the whole graph. I only did it at the ends. I'm going to say that again. When you draw a horizontal asymptote, only draw it at the ends. Do not draw it the whole way across. I'm going to say it again. When you go to draw a horizontal asymptote, only do it at the ends. Don't draw it all the way across. Okay, you get yourself into trouble that way. Okay, there it is. That's what we have so far. Katrina, does that all make sense?
Kind of. I'm kind of confused about since the numerator is less than the denominator.
The degree of the numerator is smaller than the degree of the denominator. Mhm. That's
So
K
that would be the X-axis. Oh, okay, I see.
The X-axis, this is the X-axis, right? The X-axis here, the Y-axis is here, right? So
Yes.
the X-axis has become our horizontal asymptote. Now, you don't need to know why, okay? I'm just giving you this, okay? I'm telling you this, all right? That's what happens. You just have to just trust it and take it on faith. So here's what we have, okay? This is what we have so far. We have that we know this dot is on the graph. We know that our edges have to be pulled towards these magnets. And we know that when we get to these vertical barriers, our graph has to go up or down. All right. Next step. Step 5, test points. This part really gets people, all right? This is a not fun part of the problem right here. What we need to do is we need to figure out what this graph is doing. And right now we only have 1 point. We need more points to be able to graph. So we have to pick, see where this vertical barrier is? We need to pick any point we want to the left of it. So I'm going to pick the point -3, and I'm going to circle it. That's going to be a test point. You'll see what I'm going to do with that in a moment. Then I'm going to pick a point over here, like 3, and that'll be another test point. That'll be to the right. And then I need, in here, I actually need 2 test points. I need something to the left in between these two, like -1.5. And I need something between this dot and this dot, or this vertical barrier, so I'm going to pick 0. So notice that what I did is I picked a test point on every side of the dotted line. So on each side of the dotted line, I have a test point. And in between this point and the dotted lines, I have at least 1 test point. So the way that I tell my students to do this is count how many x-intercepts and verticals do you have. So these together, I had 3 things, right? I had 1 x-intercept and 2 verticals. You will need then 4 test points. If you had 4 of these, you would need 5 test points. If you had 1 of these, you would need 2 test points. You'll always need 1 more test point than you have x-intercepts and verticals together. Look, this is the first example. If you're feeling lost, like I understand this, you got to get through a couple of examples before you start to feel comfortable with this. It's not going to happen in just the first problem. Now, once we have these test points, what we do with them is we actually figure out what the function's value is, the original function's value is at those points. So I need to go back to this and copy it and put it down here so we can see it. Here's the original function. And what I need to do is figure out what's happening at those 3 test points. So at -3, I need to plug that into this function. At -1.5, I need to see what happens. At 0 and at 3. And that means you have to plug those values into the function, all right? You have to actually plug those in here, which is going to suck, but that's what we have to do. So -3 plus 1 over -3 squared minus 4. Do you understand what I'm doing? Plugging these into the original function here? Any questions on that? You have to be careful because when you square negatives, they become positive. So this becomes 9 minus 4, which is 5. And all we care about is that this is a negative number. And you'll see why in a minute. So we plug in -3, we get a negative number. If we plug in -1.5, we plug in -1.5 and do that on our calculator, we should get a positive number. If we plug in 0, we'll get 1 over -4, which will be a negative number. And if you plug in 3, you're going to get a positive number. So I'm not showing all of this work. This you'll have to do on your calculator. So how does this help us? All we do now is we go to -3. Okay, we know at -3, we should get a negative number to come out. So I go to the left, -3, and I have a negative number come out. So I'm going to put a dot right here for my graph. -3 gave me a negative number. When I plugged in -1.5, what's right here? I got a positive number, so I'm going to put a dot here. Doesn't matter where you put it, just put it above the x-axis because it's positive. At 0, I got a negative number, so at 0, I put a dot down here somewhere. And then at 3, I got a positive number, so I just put a dot here. I really feel like I'm losing y'all here. All right or not?
I'm not gonna lie, this is so confusing.
Yeah,
Mhm.
I think we're trusting the process right now. We're just kind of watching.
Okay,
True.
I'll go
I
through
wrote down a lot
everything
of it.
again.
I
think-
started off really strong with this problem. Like it's in my notes, but then I started
Okay.
getting lost.
Well, look, we're done. It's just drawing it. Okay, so let's just go back and let's start from step one and just talk through it again so we understand what we did. The first step was to find the x-intercepts. All we did was we took the numerator, set it equal to 0, and got an answer. That's going to wind up being a point on our graph on the x-axis. Then what we did is we found the vertical asymptotes. To do that, you set the denominator, which in this case was x squared minus 4, equal to 0. There, Juliet said, okay, we'll do difference of squares. We got 2 solutions, and we remember, okay, when we draw those are vertical barriers. Then we did step 3, which is what, was it Lily, I think, or Katrina? I don't remember. Was it Lily? Sorry. We compared the numerator degree and denominator, which gave us case A, which told us that the x-axis was a horizontal asymptote. Then we put everything onto a graph. So we drew a dot on the x-axis at -1. That was our x-intercept. We drew 2 vertical barriers at 2 and -2. And then we drew a magnetic dotted line at the ends at 0 at the x-axis. So here and here, but not all the way through, just at the edges. After we did that, we picked test points. And these test points will always have one more test point than we have x-intercepts and verticals together. So we had 3 of these. We needed 4 test points. And they basically have to fill in all the gaps. Like they have to be between your dotteds and between your x-intercepts. You got to fill in every piece you don't know. That part I think people struggle with. So I will next example, I'll hopefully clarify that. We took these test points, plugged them into the original function just to figure out if it was positive or negative when we plugged it in. If it was negative, we would put a dot below the x-axis. If it was positive, we'd put a dot above. That's where we are. Can I clarify any steps on that so far?
Yes, for the, you know how you put those like the -1.5, -3, +3? I know you
Yes.
said those are test points, but at any point could we use different numbers?
Yes, good question. So they are test points. So what I was trying to do is, let me take these out of here. Let me take those points I didn't know, right?
Mhm.
Okay, so here's where we were when I picked the test points. Basically, here's what I'm thinking to myself. I need to know what the graph looks like over here. So I need to pick any point that's to the left of this dotted line. I picked -3. But if you want, you can pick -4. And if someone else wants, they can pick -5. And someone else wants, they can pick -6. As long as it's to the left of this line, you can pick it, okay? Same with the right side of this one. I needed something over here to give me an idea of what the graph looks like. So I picked 3. If you want, pick 4 or 5 or 10 or 100. It doesn't matter, just as long as it's to the right of 2. Okay, so that kind of tells me I'm going to have a test point over here and a test point over here. Now I need to know what's happening in here also, but there's a dot in here already. So I need to kind of know what's happening to the left of this dot and what's happening to the right of this dot. So there's 2 regions here I needed to pick test points. I picked 0. You could have picked 1. You just can't pick 2 or 3 or 4 because it's got to be between here. So I picked 0. And then here I picked a point between -1 and -2, which is -1.5. Does that help, Darsha? Yes?
Yes, sir.
Okay. Maybe I'll just leave that up there. Let me go back to where we were with the picture here. So here's where we are, right? We've got our test points. And now is the absolute critical step, okay? And let's see. Cheyenne, are you there? You get, Cheyenne's gonna get the hardest step? No? Not the hardest, but Tiffany? Let's see, Bela, I guess Bela, you got next, so.
What am I helping with?
Okay, now it's a matter of doing the last step of the problem, which is to use your brain to sketch. Now, what I mean by that is not like, I don't mean that in a way of like, use your brain, this is easy. It's like you have to think about what's happening here. So Bela, everywhere you see a vertical dotted line, you are not allowed to cross. And when you get to drawing, when they get to that vertical dotted line, your graph can't cross it. So your graph either has to go up or down, okay? Keep that in mind. Vertical barriers, can't cross them, gotta go up or down. Also, when you draw the edges, this is a magnet that's gonna pull your graph towards it, right? That's what these
Right.
dotted lines over here mean. And Bela, one more thing. This dot right here is the only place you're allowed to ever touch or cross the x-axis. That's the only place, all right? So here we go, I'm gonna help you. Let's start here at this point right there in yellow. I would like for you to tell me if I started to draw this out to the left, what would I have to do?
Out to the left, it wouldn't be going straight out, but it would be kind of curved going out negative. Because
Okay, like,
a way to describe it.
like this?
No. It's gonna
Okay.
go. I don't want to say it's gonna go straight to the left because it's not a straight left.
Okay, so not that.
Just like a little bit curvy.
What is this dotted line telling you?
It's gonna. I'm gonna be not parallel to the dotted line, but oh, that one.
This dotted line right here, what is that? That is a horizontal asymptote, right? What does it behave like?
Oh, I'm
I
not.
said I wanted you to-
aware.
I want you to think about it as like a magnet, okay? So as you get closer to it, it starts to pull you towards it. You see that, like that?
Mhm.
That's the behavior of this graph to the left. You don't have a choice. It can't do, oh shit. It can't do this because then it's not going towards the horizontal, right? It can't do this because again, it's not going towards the horizontal. Bela, you can't do this and then come back towards it. Why can't you do this, Bela?
We're not crossing the barrier, right? Well, it's also
Well-
wrong, but
You would cross the x-axis, wouldn't you?
right, and we didn't put that point down.
That's right. There is no x-intercept there. See, so Bela, this is almost like a process of elimination. You are forced to do one and one thing only, and that is to the left to go out to this barrier. I mean, to this magnet and get pulled. Okay. Does that make sense, Bela?
Yes.
Okay. Now to the right, Bela. If I want to continue and draw this to the right, I have a problem, don't I? This vertical barrier is in my way.
Mhm.
And Bela, vertical barriers force your graph to either go up or down. So which way is it, up or down?
I think we're gonna go down, and we're not
Okay.
gonna cross the barrier. We'll just get kind of close to it. I don't want to say parallel because that's not the right word, but
Yeah, it just approaches it, right? It just approaches. So you think it does this, right?
I think so.
Yeah, okay, now why Bela? This is important, everyone. Why couldn't Bela have done this? Because that is the same sort of thing. It's approaching but not really touching it. It's just getting closer. Why can we not do that?
Besides,
Is
the
it because it's, go ahead, I'm sorry.
oh, sorry. Oh, okay, sorry. We're still crossing the axis, right?
Yeah, because right there you would have created an x-intercept that you actually don't have. We only have one x-intercept, right? This is it right here in blue. That's the only x-intercept we have. So if Bela were to try and draw this, see, she had two choices, go up or go down. That were her two choices. But up is not an option because she would be crossing the x-axis. So it has to be down. All right. Are you thoroughly confused and frustrated yet? Bela, I'm gonna let you off the hook. Do you understand that part of the graph?
Yes.
Okay, now let's go to, let's see. Is Elisa here? Did I call Elisa yet?
Yes, I'm here.
Okay, Elisa, are you okay to help out with the next part?
Yes.
Okay, can you see the graph okay?
Yes.
Okay, do you see, Elisa, these three dots are just, I mean, these are just connected to one another. This is almost like we're back in kindergarten. We can just pull these three dots together like this. Do you see that?
Mm-hmm.
Now, to the left though, Elisa, if I start to draw to the left, do you see that I'm gonna have a barrier in my way?
Yes.
Okay, so barriers, vertical barriers tell you have to go up or down. So which way is it? Up or down?
Up.
Up. Okay, now why not down? You had a choice here. You could have gone up or turned it back down. Why not down?
Because then you'd be creating another point that you don't have.
Exactly. You'd be creating an x-intercept we don't have. This is not a matter of saying, and Elisa didn't say this, but a lot of students will say, oh, it has to go up because it looks like it's going up here. Well, that's not why. It's going up here because it can't go back down because you'll create an x-intercept. How about this one to the right, Elisa? We're coming to the right and we're like drawing, we're all happy. And then again, you're faced with a choice, up or down.
Down?
Down. Again, not because it looks like it's going to go down, but it's because you can't come back up and cross. Good. I think you can do the last one for us, Elisa. Go to this point right here and tell me what happens if I draw to the left. What would have to happen?
It would have to go up.
Exactly. Again, because it can't come down because it would cross the x-axis. Can't do that. You can only cross here. And then what about to the right, Elisa?
It would get pulled towards the dotted line.
Yep, perfect. There it is.
I had a quick question actually.
Yes.
So I understand why each point was like up and down, but how did you decide like how far up and down to put it?
Good question. So Lisa's asking on this step right here where I plugged in these values and I got numbers, all I was doing was negative, positive, negative, positive. You do not have to care about how high or low you put them. And the reason goes back to, remember with polynomials, we were doing these graphs and we didn't really know how high or low they went. I said, hey, you know, people are going to get different answers. Don't worry about how high or low your things are going to be. Remember this? It's kind of the same thing in the sense that all we care about is whether or not these dots are below or above or below or above. That's what we need to be able to draw the rest of it. Think about, let me just have you focus on one point. At this 3, what if I had put it down here? How would my graph be different? Well, it would still go to the left and go up, and it would still go down to that magnetic line, right? So basically these two are essentially the same picture. It doesn't have to be perfect. It's to get a general sketch of the graph. Does that make sense, Elisa?
Yes.
Okay. All right, so look, let's take a look at this graph. I'm going to go to this graphing software and I'm going to graph it here. X plus 1 over x squared minus 4. There's their graph. Okay, there's their graph. And here's ours. Okay. So do we have the same general behavior? We both have an x-intercept right there. That's this guy right here. We both have that x-intercept. To the left, it goes up. To the right, it goes down. We have that. And then over here on the left side, it does this thing. We have that. And then over here on the right, it does the same thing. Okay. So that's pretty much it. We still have a lot to do with this, and there's no way that one example is enough. But I have some kind of good and bad news. It depends on how you want to look at it. So today is my wedding anniversary, and my wife surprised me by taking the day off and didn't tell me. So she's not working and didn't tell me she's not working. And I was like, well, I'm working. So I told her that I would do like my office hours and then I would do the first half of class today and then I would end a little early. So I hope y'all don't mind, but I'm going to give you a problem to do for homework because we've spent a lot of time and you still are kind of not really ready for like a whole homework assignment on this. So what I'd like to do is give you two problems that are pretty much going to be exactly like this. And what we'll do is we'll discuss those next class. So the two problems I want you to do are, this one's going to be very similar to the one we just did. Okay. Let's do x over X squared minus 2x. I want to make sure this works. Minus 15. Okay. That one will be very similar to the one we just did. This one is a little bit more challenging. Hold on, I don't know if I can give you that. Yeah, I can't. Gotta do something else to it. I want to make sure this works, so hold on. Okay, yeah, we'll do that. Okay, so here's what I'll tell you on both of these. These are both going to work pretty much the same way the one we did in classes. When you get, oh, well, I'll put this back up here. You know how when we got to that step where we said horizontal asymptote case A, B, and C, and we did case A, right? Both of the problems I'm giving to you are case A. So that means I haven't shown you how to do case B or C yet. That'll be next class. So both your homework problems will require that you do the same thing. So you're going to have x-axis as a horizontal. The first problem, again, very much like the one we just did. This one's a little more challenging. So why don't you just see how you do on this? It's not like I'm going to take it for a grade, but it would help tremendously if you try and work through those on your own, okay? And then we'll start class next time by, going over those, answering questions. I'll probably start class by just like showing you the graphs of these that I did by hand, and then see if you can get the same thing. All right. Okay. Well, I appreciate your attention, and I appreciate y'all not giving me grief about ending class early. I know that, I'm not
Can you
gonna
upload this video?
Pardon? Yes,
Like when we
I'll save
end
it right now and
the-
I'll upload it. Yeah, because you may need to go back and watch this for sure.
Thank you.
Okay.
Are we supposed to send the answers for these with the other ones?
No, these I'm not going to say are required because by me doing just one example, I'd feel bad saying you have to do these and turn them in for a grade. This is more of practice this. If you feel like you can get this done and do okay with it, I think you'll be ready for the next step with these. Okay, everyone, enjoy the rest of your day. I'll upload the video right now, okay? Well, as soon as it comes to me through Zoom.
You didn't send the Dropbox link, right?
I did, or I will. What did you say?
You did not send the Dropbox
I did not. I
link.
will send it. Yep.
Okay.
Okay. And that'll,
I wanna
because I
ask
got the
the-
problems from last time. Those will be due before class. Yes. Okay, everyone. Have a great day.
Thank you, you too.